Yesterday you learned about the discovery of the electron in 1897 by J.J. Thomson. He used a device called the cathode ray tube to measure the charge to mass ratio of these mysterious rays that were emanating from the cathode of this cathode ray tube. Thomson had already established, by virtue of the fact that they deflected in a magnetic field, that they were negatively charged particles, but by measuring the charge to mass ratio to be 1.49 times 10 to the 11 coulombs per meter, by measuring it to be such a big number, bigger than any other charge to mass ratio ever measured, he deduced that these negatively charged particles must be subatomic. He called these negatively charged subatomic particles electrons. This is the first recognition that there is something smaller than the atom. But remember, at the end of the day, he knew what the charge to mass ratio was, but he didn't know what the charge was, and he didn't know what the mass was. Now enter Millikan. Robert Millikan performed an experiment called the oil drop experiment with a basic setup looking like the diagram on the right. He had a battery with a positive terminal and a negative terminal attached to two parallel metal plates. With the way that I have the battery set up, that would make the top plate positive and the bottom plate negative, but it could have been the other way around. It doesn't really make any difference. The electric field between those plates, the way that I have it set up, is going to be downward from the positive toward the negative. Now, Millikan injected tiny little oil droplets in between these plates. These tiny little oil droplets came from something called an atomizer, which is basically like a perfume dispenser. You have liquid perfume in a perfume dispenser, and you spray it, and the perfume becomes atomized. The particles become really, really, really small. If we do the same thing with oil, then we get these really, really, really small oil droplets in between these charged parallel plates. Some of these oil droplets might be charged by friction, some of them may not. You may have to charge these oil droplets by irradiating with X-rays. In the end, it doesn't matter how they become charged. What we're looking at is the charged oil droplets in between these plates. Tiny little oil droplets that you can't even see with the naked eye in between these plates. I want to look at both types of charges here, the positively charged oil droplets and the negatively charged oil droplets, but first let's look at the negative. There are two forces that act on this negatively charged oil drop. There is firstly a force of gravity acting down, because gravity acts down on anything with mass. And in this case, there is also an electric force acting up. It's a negatively charged particle. The electric force acts opposite to the field. Remember that from Unit 2. Electric force on a negatively charged particle is always opposite to the field. On a positive charged particle, it's always with the field. Now, we don't know how big that electric force is, whether it's bigger or smaller than the force of gravity, so we don't really know how long to draw that vector, but we'll just draw it roughly the same length. Now, if these negatively charged particles end up being suspended, in other words, just end up sitting there in midair, then that means that this electric force and the gravitational force are equal. They balance each other. The other scenario that could happen there is that this charged particle could go at a constant speed. If that's the case, if it moves up or down at a constant speed, then these two forces have to balance as well. Now, there are scenarios where these two forces don't balance. That's going to cause the charged particle to accelerate, but we'll look at that in a few minutes. For now, let's focus on these oil droplets that are either suspended or traveling at a constant speed. The electric force acting downward must be equal and opposite to the gravitational force, the electric force acting upward must be equal and opposite to the gravitational force acting downward. They got to balance. Now, if you remember from Unit 2, your electricity unit, the electric force is Q times E, the electric field, and the gravitational force is M times G. Millikan would have rearranged this equation, solved for the charge, remember, not the charge of an electron, but the charge of an oil droplet. He would have known the mass of the oil droplet by density calculations, knowing the size of the oil droplet, knowing the density of oil, he could have found the mass of the oil droplet. He knows what G is, it's 9.81, and he would have known what the electric field was because he was controlling the electric field. He decided how much electric field needed to be there. When he measured the charge of an oil droplet, he would have gotten perhaps something like this. 3.2 times 10 to the minus 19 coulombs. He does it again, and maybe he gets this one, 9.6 times 10 to the minus 18 coulombs. He does it again, maybe he gets 1.6 times 10 to the minus 19 coulombs. 1.6 times 10 to the minus 17 coulombs. 3.2 times 10 to the minus 18 coulombs. Maybe 6.4 times 10 to the minus 17 coulombs. When he did this hundreds of times, he found the charge of hundreds of different oil droplets by repeating the experiment hundreds of times. He found that all of these charges, all of these oil droplets, either had a charge of 1.6 times 10 to the minus 19 or a multiple of that. This one is twice that charge. This one is 60 times that charge. This one is 100 times that charge. This one is 20 times that charge. And this one is 400 times that charge. They're all multiples. They're either 1.6 times 10 to the minus 19 or multiples of 1.6 times 10 to the minus 19. And that led Millikan to two conclusions. One, there is an elementary charge. The elementary charge, the smallest possible charge that you can have. And its value is 1.60 times 10 to the minus 19 coulombs. Now, since the electron is a negatively charged subatomic particle, Millikan deduced that that must be the charge of the electron. We already knew that it was a negatively charged particle, and now we know that its charge is negative 1.6 times 10 to the minus 19 coulombs. He also established that charge is quantized. What does that mean? Well, it means that you can have the elementary charge, or you can have 2 times the elementary charge, or you can have 74 times the elementary charge, but you can't have 2.7 times the elementary charge. You can only have the elementary charge or a whole number multiple of the elementary charge. Money is quantized. In Canada, you can have 5 cents, or you can have a multiple of 5 cents, but you can't have anything in between. You can't have $6.97 anymore. You can have $6.95, or you can have $7. Charge is quantized. You can have 1 electron, or you can have 74 electrons, but you can't have 2.7 electrons. We'll take a look at what happens to charges that are accelerating in just a few moments. But I want to look at an example problem first, looking at an oil drop that is suspended. This one says, a Millikan-like oil drop experiment is performed with an oil drop that has a mass of 4.89 times 10 to the negative 14 kilograms. There's an electric field that exists between 2 charged parallel plates with the top plate being positive and the bottom plate being negative. What's the number of electrons gained or lost by the oil drop if it is to be suspended in the electric field? Let's draw this out here. We have a top plate that is positive and a bottom plate that is negative. We have an oil drop here. We don't know whether that oil drop is positive or negative, but we do know that the electric field points downward from positive to negative. We know it's suspended. That must mean the force of gravity is acting down, and the electric force must act up. Otherwise, it wouldn't be suspended, right? All right, so how do we analyze a charged particle, an oil drop that's suspended? We say Fe equals Fg. We say QE, the electric force back from our electricity unit, is equal to m times g. Now we're going to solve for Q. It's not the number of electrons, that's charge, but we'll find the number of electrons after we find the charge. What's our mass here? 4.89 times 10 to the negative 4. multiply that by 9.81, and divide that by the electric field strength, which is 5.0 times 10 to the 5 newtons per coulomb. We do that, we get a charge here of 9.59 times 10 to the negative 19 coulombs. There's my charge. Now, how do I find the number of electrons given the charge? You guys know this from back from Unit 2 as well. Whenever you're finding a number of anything, it's always the total amount divided by the amount for one. In this case, the total charge divided by the charge for one electron. 9.59 times 10 to the negative 19 coulombs divided by 1.60 times 10 to the minus 19 coulombs gives us 6. There are 6 electrons gained or lost. Now, gained or lost. Is it positive or negative? Well, if the electric force on this oil drop is up and the electric field is down, then that must mean this oil drop is negative. Again, remember back from Unit 2, if we have a charged particle in an electric field and it's negative, it experiences a force opposite to the field. This must be a negative particle, and if it's a negative particle, that must mean that it gained electrons. Right, this charged particle doesn't become negative by losing electrons. It must have gained electrons. Now, look at this again. Okay, it's important to draw this diagram here, right? You're never going to get this. You're never going to establish whether it's electrons gained or lost if you don't draw this diagram. We know that there's an electric field pointing downward from the top plate to the bottom plate because the top plate was listed in the question as being positive. We know that we have an electric force upward. It has to be upward, otherwise we wouldn't have this charged particle being balanced, being suspended. If the electric force is upward and the field is downward, then it must be a negative particle. All right, I'd like you to take a look at worksheet number 23 right now. 5 questions on that worksheet. I'd like you to take a look at the first 3 questions. All right, what happens if we're looking at a charged oil droplet, positive or negative, that is accelerating now? It's not suspended, it's not traveling at a constant speed, it's accelerating either up or down. That means the forces must be unbalanced. In the case of the negatively charged oil droplet, maybe the electric force is bigger than the gravitational force, maybe it's smaller. In the case of the positively charged oil droplet, we have a force of gravity acting downward, but because it's positive, the electric force is in the direction of the electric field. It's also pointing downward. We have 2 forces pointing downward now. How do we analyze either one of these problems where the forces do not balance each other? Well, we do the same thing as we did back in Physics 20. When we have 2 forces that don't balance each other, we say the net force is equal to the sum of the forces. In this case, it would always be Fe plus Fg, the electric force pointing whichever way, plus the gravitational force that's always going to point downward. Now, in Physics 20, we said the net force is also equal to the mass times the acceleration. Electric force is Q times E, like it was for the suspended oil droplets, and gravity is M times G, like it was for the suspended oil droplets. Now we just sub numbers in. Sub our numbers in and solve for whatever we're looking for. Usually that's going to be Q. When we do solve for Q, we end up getting a charge that is, well, either 1.6 times 10 to the minus 19 coulombs or some multiple of 1.6 times 10 to the minus 19 coulombs. This leads Millikan to the same result that he got for the suspended oil droplets. It's just a little bit harder to do the experiment because it's harder to measure the acceleration of the oil droplets than it is to deal with an oil drop that is just suspended. But we end up getting the same results that lead us to the same 2 conclusions. One, that we have an elementary charge that's equal to 1.60 times 10 to the minus 19, and of course the charge of the electron is that elementary charge. And 2, that charge is quantized. We can have one elementary charge, or we can have 35 elementary charges, but we can't have 2.7 elementary charges. All right, let's do a question like this now. This is example number 2. We are missing a piece of data in example number 2 before we start. This question should have said that the electric field points downward. Now, let's look at the rest of the question. It says an oil drop with this mass, 5.5 times 10 negative 15, accelerates downward at a rate of 3.2 meters per second squared. I'm going to draw attention to this because the fact that it accelerates downward makes this a negative value. You don't want to miss that. Calculate the charge in the oil drop with the distance between the plates is 11 millimeters, which we want to convert to meters, and the potential difference between the plates is 833 volts. Let's draw a picture for this one. We have an oil drop right here. There's an electric field, we're told, pointing downward. We know that we have a force of gravity acting downward, because it always acts downward. And in this case, we know that we have an electric force acting upward, but smaller than gravity. How do we know that? Well, if it accelerates just because of gravity, it would accelerate downward at 9.81. It does accelerate downward still, but less than 9.81. So something, that something being the electric force, must counter that gravity. It's got to be the electric force pointing upward, but yet it's got to be a smaller value than gravity, otherwise it would accelerate upward. All right, let's go to our next step. Our physics 20 step. F net is equal to the sum of all the forces, Fe plus Fg. M times A is equal to the sum of those forces. Remember, we're replacing the electric force with Q times E and the gravitational force with M times G. Now let's sub some numbers in. And as we do that, let's remember to pay attention to direction, positive or negative, up or down. First, let's get the electric field. We don't know what that is, but we can find it pretty easily by using our old parallel plate equation. We say 833 volts divided by 11 millimeters, or 11 times 10 to the minus 3 meters, gives us a value for electric field of 75727.2727 volts per meter. Now let's sub that in. We have 5.50 times 10 to the negative 15 kilograms for the mass. The acceleration is negative 3.2. Charge is what we're looking for here. The electric field strength is 75727.2727. Mass is, once again, 5.5 times 10 to the minus 15 times gravity, which is 9.81. We're going to make this negative because we know that gravity acts down. And we've already basically made the the net force negative by putting the negative in for the acceleration. When we solve for the value of Q here, get this as a negative number, get this as a negative number, take it over by adding, solve for the value of Q, and we end up getting 4.80 times 10 to the minus 19 coulombs. 3 elementary charges. But is it positive or negative? How do we determine whether it's positive or negative? Well, the electric field is pointing downward. The electric force is pointing upward. If the force is opposite to the field, then this oil drop must be negative. So this would be technically negative 4.8 times 10 to the minus 19 coulombs. Remember to draw that diagram. You can get the 4.8 times 10 to the minus 19 perhaps without drawing the diagram, but you're not going to determine whether it's negative or positive without visualizing, without seeing this diagram, the electric field direction, the electric force direction, and so on. Now I would like you to take a look at the last 2 questions on worksheet number 23, questions 4 and 5. Give those a shot, please.